Humans, but also robots, learn to improve their behavior. Without existing knowledge, learning either needs to be explorative and thus slow, or to be more efficient, it needs to rely on supervision, which may not always be available. However, once some knowledge base exists, a robot can make use of it to improve learning efficiency and speed. This happens to our children at the age of around 3, when they very quickly begin to assimilate new information by making guided guesses of how this fits their prior knowledge. This is a very efficient generative learning mechanism in the sense that the existing knowledge is generalized into as yet unexplored novel domains. So far, generative learning has not been employed for robot, and robot learning remains a slow and tedious process.
The goal of the Experience project is to devise a framework that will improve learning in robotics and can be applied at different levels of the robot's cognitive architecture. So we introduced the concept of structural bootstrapping. This is an idea taken from child language acquisition research to define generative mechanisms which use existing robot experience together with new observation to enrich the robot's knowledge with missing information about object, action, and planning entities.
In this scenario, we use the example of rearranging the room, setting the table for 2 people, and preparing salad, and show that the robot can efficiently acquire new knowledge about planning operators, objects, and required actions by structural bootstrapping.
Hi, Armar.
Hello, how are you?
I'm fine. I want to have dinner with Katja. Can you help me to prepare the table?
Okay, I will do it.
Given a spoken utterance, the natural language understanding component generates a goal for a symbolic planner. The planner goal is passed to the object and location replacement component that uses existing knowledge in the robot's memory to check for each object in the goal, if this object and its location are in the domain description generated from the robot's memory. The goal is passed to the planner together with a domain description generated from the robot's memory. The planner generates a plan. The plan execution and monitoring component triggers and validates the execution by the state chart framework of ARMAR-III.
Let me get the cups.
For grasping, the robot autonomously selects an optimum view direction for the current task based on the position uncertainty of the object and the hand. Visual servoing is used for grasp execution. The planner informs the robot where to place the object. ARMAR-III is now checking that the place where the object should be put is empty. The hand with the object is moved downwards to the desired placing location, and the object is released once contact is detected.
Put the salad bowl on the sideboard.
Okay.
If ARMAR cannot find the required object, the object and location replacement component is evoked. It replaces missing objects with alternatives. It is evoked after the language understanding component produces a goal for the planner, or if plan execution fails because of a missing object.
Oh, the salad bowl is not here. But what is this object in front of me? Can I use it instead?
Different replacement strategies generate replacement candidates from a variety of input data, like object shapes or text corpora. The shared visual feature strategy uses a pre-computed database of object shapes and their affordances. During runtime, the affordances of objects currently in the field of view are extracted from point cloud data based on their visual features. These affordance labels are then compared with the affordance labels of the missing object to find a suitable replacement candidate. For example, one container can be replaced with another based on their shape that suggests pouring something into it.
ARMAR, help me to prepare a salad with corn and oil, please.
ARMAR-III searches for the location of the required object in its memory. First, it checks the places where this object has been seen in its previous experience. Then it considers the typical location of the object, which has been extracted from text corpora. Corn is not found in any of these databases. Therefore, the robot asks the human for the additional information.
I do not know where the corn is. Can you tell me?
The corn is in the fridge.
Okay.
The robot's memory has been updated, and now a new plan can be generated. If a required object is not reachable or graspable to the robot, then it asks the human for assistance.
I cannot reach the whisk. Can you please pass it to me?
Here you go, ARMAR.
The robot closes its hands once contact and force in the hand is detected. The robot has executed the stirring skill based on the wiping action it previously learned through human demonstration. It adapts the wiping skill to the new hand orientation required for holding a stirrer.
ARMAR, put the orange bowl on the table.
Okay.
Clean the sideboard, ARMAR.
Okay. Could you please pass me the cleaning cloth?
Sure thing, ARMAR. Here you go.
What a mess. I will clean it.
The robot has learned the wiping skill from observing humans. The movement observed has been encoded as a periodic dynamic movement primitive. This primitive can be parameterized in order to reproduce the wiping action for different surfaces, locations, frequencies, and amplitudes. Based on force feedback, the robot adapts the learned wiping primitive to the current world state.
Arrange one chair armor.
Okay.
Good.
Based on the robot's reachability map, a feasible position for approaching the chair is estimated. A bimanual pushing action is executed to move the chair to the target location while avoiding obstacles.
ARMAR, bring us some soda.
Sorry, I have no soda, but I can bring you multivitamin juice.
Another possibility for an object replacement is using the common sense affordances strategy. It employs typical object affordances generated from textual corpora. It extracts probabilities of nouns occurring as certain arguments of verbs and generates a database of affordances for objects. This database is used afterwards to compute similarities between objects in the context of affordances by employing a machine learning algorithm. For example, soda can be replaced with juice towards the affordance of drinking.
Yes, that's also fine, thanks.
Okay.
Potential object replacement should be confirmed by the human.
Oh, the juice is not here. Where else could it be?
If the required object has not been found at the assumed location, the common places strategy uses the feature of the ARMAR-X architecture that allows robots to learn typical locations of the objects from experience. Whenever an object is localized, the database is updated and the probability distributions of object locations are adjusted. The replacement strategy can query this database for most common places.
Found it. Here you go.
Thanks, ARMAR.
The robot offers the object to the human and waits until a force is detected, then the object is released. Based on its experience, ARMAR was able to replace missing objects and infer common object locations to perform a task. In the same way, ARMAR is able to replace actions with semantically similar ones.